Hello? Hello, I'm online.
Are you going to do this assignment now, or can we ask other questions in the meantime?
Yes, okay. Which assignment? Can you see my screen?
Yeah.
Yes.
Because I've got a question regarding the slides from yesterday.
Slides from yesterday. Just 1 sec. I'll try to open. It's a morning lecture, or is it afternoon lecture?
Afternoon, lecture 5.
Lecture 5. Okay, just 1 second. Yeah, here we are.
Yeah, brilliant. It's regarding slide 16.
This one.
Yeah. So it's just a quick question. So that is connected with the slide above, slide 15.
Just 1 second.
And
yes.
Exactly. Yeah. So I understood that. Well, from what I understood, you have to use the formulas you've got there for delta B and delta C in 2, 5, and 4, and then put them into the formula on the slide below.
Yes.
Am I correct in saying that?
Yes, exactly. I consult the table, and then from the table I pull out these values, which gives me the displacements at points B and C in the loading case 2, 5, and 4.
Yeah.
And then I take these things, and they are provided with the signs, plus and minus is just simply whether it's upwards or downwards, given the direction of y. And then I just put these things into these compatibility equations. And by doing so, I set up the system of 2 equations with respect to these 2 unknowns, which is RB and RC.
Okay, well, the first line, delta B there, equal to a third RBY, A cubed, etc. Is there not a mistake in that? Because I couldn't quite get it to work in terms of the 3 values that were given for delta B. So as far as I can see, don't match with the values that are on the formula there.
Yes. So you see, the story here is in the real life, the point B is has displacement due to the action of these 4 free forces, right? So point B in the assembled system like this. Then you have the displacement point B due to Q, R, B, and RC. Then you consult this table, and then you see that the point displacement of point B due to the action of Q is this amount. Due to the action of force R, By is this amount, and here all you have to do is just to replace letter P with letter R, By, and the same goes for the third one.
If we could just go through it together then on the slide below, because I'm a bit confused, because it looks to me as if there's been a mistake, that you've taken one of the values for delta C instead and put it in the formula for delta B.
Oh, just let me see. Just 1 second.
If that is the case, then I think I understand it. I'm just a bit confused because it.
Yeah. So just let me see. So we have for point B, this is this guy, and this guy.
I think it's the delta C.
Oh yeah.
2.
Oh, yeah, you've taken a value from delta C. Yeah.
Yeah. So this is So this is, I think, just let me. So the first one is definitely correct.
Yeah.
Then we have this one of the 3, which is, I think, also fine. And then we have this 1 over 24 a squared.
Which is then. I presume that's delta C2.
I think you're right. I didn't. You see, to be honest, I didn't check this this formula, but I understand that it can be confusing.
It's a tad confusing, yeah. But no, if that is the case, then it makes perfect sense. I just wanted to check that was right before I
Okay. Thank you very much, and sorry for that. But you see that then you prepare the slides. That very often you just sort of do it a bit too quick, and then.
Oh yeah. Well, no problem at all. I just wanted to check just in case, but
Yeah.
No
Thank
worries.
you for pointing me out.
That's all right. Oh, thank you anyway.
Good. Thank you.
Sergey?
Yeah.
Is there any chance you could go through the first assignment from the afternoon lecture yesterday?
It's no, it's not this one. It's this one.
Yes.
So the very first assignment, or a bit low, because I think this first assignment, I think we have sort of discussed it. So this assignment.
Yes. So I think I understand what is happening, but I don't understand how we arrive at the equation.
Which one? Because here I think you the number. So equation number 1 or number 2?
How do we get to equation number 6 from equation 1?
So equation 1 stands alone. So then this is something which we use but in the end. So what happens is that we have this compatibility condition of that the displacements are the same. Then we use the Hooke's law to express these displacements via forces. And then we take this equation 2 and then find the relation between the forces P1 and P2. And then they take this relation and substitute it into the equation 1. So we can say, we can do it in both ways. First, we can just say, okay, we're interested in this force PS. So we say that PS equals PB, and then AS divided with EB. Substituted to the equation 1. And isolate PB. Or we can do other way around. We can, in the equation 4, we can isolate PB, express PB via PS, and then take this expression for PB, again substitute to equation 1, and then it gives you formula for PS. And then you just so this is your solution, and you do kind of the sanity check. You just take this PS, substitute from first equation in equation 5, substitute it to the first of equations 3, and you've got the result. And then you take the second one, substitute to the second, and of course you get exactly the same result. So this equation 6 is a kind of a sanity check. But the point is that you use this equation 4 in order to solve equation 1. You can it will be also sort of fair to say that you have to solve the system of 2 simultaneous equations, equation 1 and equation 4, with 2 unknowns, PS and PB.
All right, thank you.
Good.
Can you maybe explain as well in the B part how you derive that equation for sigma sigma S and sigma B. No, on the same page, just in the last part.
Here, so how the stresses are calculated?
No, actually I was meaning down at the allowable load.
Allowable load. Okay, so you see what, this is very reasonable. So what happens is that as we have found displacement as equation 6, then we can find the stresses. So as we found PS and PB, we can immediately find the stress in steel and stress in brass, and they're defined by formula 7, and they're not equal, right? They are different. So then we say we are provided with the allowable stresses. We know that for steel, the allowable stress is 180. So then we just, and we are provided with Young's moduli and areas. So this is what we know. So then we just ask ourselves, so what should be the force PS if we have the stress equal 180? And then not PS. So, okay. So now I see what was the. So here this is a typo. So in the section B, I understand your question. In the section B, this PA, PS, and PB, this is wrong. So this is just P. Okay. So this is just a typo in the solution. Because what we do, we just say, so we have the allowable stress in the steel is this amount, 180. So then we just we just take the first of equations 7, and then we isolate P. And then you can immediately see that if you substitute in this equation sigma equals 180, so it's then sigma s, then you just invert this fraction, so ES plus B divided with ES. So then you have this quantity, and then you have here this P equals this, and then the true interpretation is that if we allow the stress to be equal 180 in the steel component, then the total force must be 7.07 kilonewtons. Then we take the brass part, and for the brass part our allowable stress is 250. Then we say, okay, so if we let the stress in the brass part be 250, what would be then the force which produces this stress in the brass component? And the answer is 11 kilonewtons. And then we have here these two results. So to have the allowable stress in the steel component, the force must be 7.07, and to provide the allowable stress in the brass component, it must be larger. So it means that we have take as allowable force smaller out of these two. Because if our total force will be 7.07, then we hit the limit in the steel, but we're still quite safe in the brass.
Sergey, where does the 250 megapascal come from? Because I think the text says 140. That I'm a bit confused about that.
Yes, just let me see. This is a very good question. So here indeed it says that in brass is 140. Yeah, so now okay, so probably the simplest thing will be, so if you take your pencil and if you just cross out this statement, and in brass it's 140, and instead you put 250. Then
All right.
it will be consistent.
Okay, super.
And I'm just sort of puzzled because I think that these solutions, it looks like these solutions are in the same format, in the same kind of style of writing as the book itself. So probably it's in the book, and then the only explanation I may come up with is that probably it's kind of the conflict between two different editions of the book, because they have a very sort of a fancy manner to change the exercises, to change assignments, in order to sell more sort of the books. And then sometimes probably they forget to change the solutions. So it's purely technical. So the easiest will be just to cross out 140 and put 250 in the formulation of the problem.
I'll do that then.
Thank you. Sorry for that.
Sergey, could you maybe explain how we arrive at how do we substitute force over area with these other entities in equation 7?
Yeah, so you see, we have found in this way, we have found the forces. So more precisely, what happens is we have the total force P, and this force P is distributed between the steel component and the brass component. Then by this means we found what is the total force which is sort of taken by brass, and what is the total force which is taken by steel. Now we come to the next point. What are the stresses in these two components? And to do this, we have to divide the force acting in steel component by the area of the steel component, and take the force in the brass component divided by the area of the brass component. So then this gives us these expressions for the stresses in the steel component and in the brass component given in the formula 7.
Okay, so just to be sure that you can you can determine the force acting on the steel by saying the E module times force.
Yes, so this is a definition of stress. So no. So the E module has nothing to do with this. The E module is involved in equation 5, because in equation 5 we have the partition of the total force between brass and steel, and it's defined by this formula 5. So this is the total force in steel, and this is total force in brass. And then as we go to the stresses, we just go to the intensity of the force, which is the stress in steel, sigma. And here, of course, it would be more consistent to put here sigma S. And then in brass, and then it will be sigma B. So the partition of the force is defined by formula 5. And formula 7 is just more detailed view on what happens in steel and what happens in brass. Make sense?
I have a trouble seeing how. So the equation says force over area. How that gets transformed into E module times force over.
Yeah, but you see, so it's very simple. So please just take a closer look into the equations 5. Equations 5 is the answer for the system of these two equations written above. And then you can immediately see, looking at the dimensions, that you can take this P sort of out of this fraction, so that you can say that you have ESAS divided with ESAS plus EBAB times P. So what it tells you is that the fraction of the force P which comes to the steel is the ratio between the stiffness of the steel component, and AS is the stiffness of the steel component, to the sum of the stiffnesses of steel component and the brass component. So this is just the coefficient. And then if you take this expression and divide the cross-sectional area, it looks like you take the Young's modulus and multiply by the force. But indeed, it's not the case. You just take, you can take this ES in formula 7.1 and put it in the denominator. Then you have bare P in the numerator, and in the denominator you'll have just AS, which is area, which makes perfect sense, plus ratio of Young's moduli times area of brass component. And then it will immediately remove your confusion with the multiplication of Young's modulus times force.
All right.
Because the true place for Young's modulus is in the denominator. And then you have just AS plus AB over AS times ES, EB over ES times AS. You see my point?
Yes, so you should be able to find equation 7 exclusively from equation 5?
Yes, so equation 7 is definitely the follow-up from equation 5. So what you do is just you divide the PS, you divide with the AS and get this formula. And then sigma B is PB divided by AB. Yeah. So it's straightforward follow-up. 7 is straightforward follow-up from 5. And 5 is the solution of the problem of defining PS and PB. More questions? I'm online. I'm online.
Sergey,
Yeah.
I have a question regarding the solution in the first lecture, assignment 5.510.
Just let me see the first
And
lecture.
I sent a screenshot in the chat.
Just probably it's better if I says the first lecture. Oh, probably it's better to go for it. Just 1 second. We go. So solutions. Yes, so which one? Can you see my screen?
5.5.10. So that one. Yeah.
So this is about this kind of the bending. So
Yes.
we have the a slipper, and then we have two forces from the wheels, and then I have uniform distribution of friction. Yes.
Yeah. And then I'm having trouble figuring out where M2 and M1, where the formulas come from.
So this is from this shear force and bending moment diagrams.
Yeah.
So then what we have to do, we return to this picture, and then we say that we have the x along the length, and then x is 0 here, and then x equals a here, x equals a plus l here, and x equals l plus 2a here. So then we do this kind of the chopping and balancing. So first we do the cut here. You see my cursor, right? You do the cut here, and then you just sketch this small piece, and this piece is loaded by uniform load, and then at this cross section you have the moment acting in this direction. And then you just write the formula for the moment, and it will be qx squared half.
Okay.
And then you come to the point then x equals a, to this point, and then you substitute instead of x, you substitute a, and you get this result, qa squared half. Yeah, so in principle, so what is I don't have this this device just to write using the mouse or something. Of course, I can. We have this whiteboard, but it's to the. But I'm sure it's actually it's very simple.
Yeah, that's why it annoys me that I don't understand.
Yes. So you see. So now let's take a look at this. So just take a sheet of paper and take a pencil, and then you just show me from time to time what you sketch. So you sketch first the small part of this slipper between 0 and a. So just very small part. And then you apply this uniformly distributed load on this part, and then you have to designate that the length is x. And then we follow our sign convention, and you apply the moment m as a function of x, which rotates anticlockwise. So now just show me this picture. So if you just bring it, show it to the camera.
Yeah. 2 seconds.
Perfect. That's correct.
Yeah.
And now we just say the yes. So now continue. So now we just take the sum of the moments with respect to the right edge of this, of what you have shown, right?
Yeah.
So then you just say that sum of the moments equals moment at x, and it's with plus because it rotates counterclockwise, right?
2 seconds. So, can you repeat the last 10 seconds?
So you just put, you say that you have a sum of the moments around point, yes, so around this point there you have cross section. So just
Yeah, the right side.
yes. So then you, as you have it, then you have this mx with plus, and then the distributed load gives you the force with minus, right? The moment with minus.
Yeah.
And then it must be 0. So then you isolate mx, and you obtain x equals 0, x equals a, and then you obtain that the moment equals qx squared half.
So
Just
I have
I'm just yeah.
this.
So, but no, because here you have to calculate the moment, which is produced by this distributed load, and the moment produced by this distributed load at this part of the beam, it's qx, which is the force resultant, multiplied with x half.
Oh yeah. Yeah. So like this. Do you see?
Yes, but then you have to take this q times x. This is just the force resultant. But now you have to multiply by the arm.
Huh?
No. Just take your time. You see, you are a bit too fast because you have the intensity q. The force resultant will be indeed, as you wrote originally, you have q times x. So this is the force resultant, right?
Yeah.
And then you take this force resultant and multiply with the arm.
With the arm.
Oh,
the arm. Yeah.
Yes, the arm is a half of x.
So that's
Yes, and it must be 0.
Okay.
And then, of course, you forgot minus in front of q because this is rotation clockwise.
Yeah. And then I isolate mx.
And then you have, for mx, you have a formula qx squared half.
Yeah.
And then you plug here x equals a, and you get the formula which is presented in this in the solution.
Yeah. Then it adds up in my
Then
head.
you do the next cross section. And then for this next cross section, you do exactly the same things, but now you have also force P in the game.
Yeah. So the next cross section is
between forces P. Somewhere in between.
Can I point?
So the next cross section will be somewhere here.
Oh, okay. Yeah.
Oh, I mean, it's somewhere here.
Yeah.
And then you do the same drawing, exactly the same drawing. The only difference is that now you also have this force P.
Yes. I get it.
And you'll get all these results.
Yeah.
Okay?
Thank you.
Good.
I have a question regarding the lecture today. The Wöhler curves, are they made both by the low cycle fatigue approach and the high cycle fatigue approach, or is it only the high cycle fatigue?
So in principle, they're valid for high cycle fatigue. But in principle, you can also do this kind of things with the low cycle. But you are right, so they are plotted for the high cycle fatigue. And you see, if you take a look at the slide 8, I show it on my screen. You see it is chopped at 10 power 3.
Yeah.
So I think it will be fair enough just to say that these Wöhler curves are plotted for high cycle fatigue.
Yes, okay. Perfect. I have one more question, but that's maybe going to take some time, because I was wondering if you maybe could try to talk us through the concept of that fatigue damage, that Palmgren and minus damage rule. I think I was a bit lost in how to convert the Wöhler curve onto that one.
Okay. So the idea, in order to grasp the idea, let's just take a look at this. Can you see my screen?
Yes.
Okay, so I'm after this knee part. That's a little bit easier to explain. So what we have is that we have this red line, the Wöhler curve, which is a division line between the possible combinations of number of cycles and level of loading, and impossible. Impossible meaning that if your point is somewhere here, then it's impossible to have this amount of cycles at this amount of loading without failure. So here we have failure, and here we have no failure. Then the common sense probably tells you that if you have the combination of level of loading and number of cycles somewhere here, then your specimen is relatively far from its death, because in order to kill your specimen, you have to travel with the same level of the loading. You have to travel horizontally until you cross this red line. Does that make sense?
Yes.
Because this is actually, so if you have grasped this idea, then the next thing is very simple. So now we just say that if we have no cycles, then we have no damage, and then the capability of the specimen is it's fully capable to withstand loading. So now if we, for example, if we come to this point, it means that we have already used off some of its the capability to withstand the loading. And then if we come to the red line, this division line, then we took it all. So we completely exhausted the the possibilities to resist the loading. So then the damage here is 1, and damage in the beginning is 0. So then the linear concept of damage is that if you are halfway from n equals 1 to this red curve, if you are halfway, then you used half of the sort of the capability of the specimen.
Okay.
Does it make sense?
Yes, that makes sense.
Good. So now we make the next step, and now we just say, so let's imagine that we introduce small n cycles at this level, and small n2 cycles at this level. Then if we have standalone regime with n1 cycles, we have used sort of this amount of its capability. And this is n small 1 divided by n capital 1. If we now go to the second regime, there we have this n2 small cycles. Then we do the same thing and we see how many cycles actually is needed to kill this specimen. And then we say that this n2, n small 2 divided by n capital 2 is the damage which we have sort of we have brought in the regime number 2. And then if we put together these two numbers, n small 1 over n capital 1 plus n small 2 over n capital 2, we see how much damage we have inflicted on the specimen using these two regimes.
Okay.
Make sense?
Yes, it makes more sense. So this one, we only look at beneath the red line when looking at it.
Yes. So this is the point. So the point is that if you do loading at this level, then you kill your specimen at this number of cycles. It's n capital N1.
Yeah.
But if you stop somewhere here, then you have not yet killed it, but it's sort of it's wounded, so to say, to some amount. And then if you change regime to the lower number of lower level of loading, then you need more cycles to kill it.
Yeah.
But then again, so if you just see how heavy is the wound you sort of use.
Yeah.
You sort of provoked by second regime. And then if the sum is mortal, then specimen is dead.
Yeah. Perfect. Thank you.
Good.
Sergey, you said something about if n, even if n wasn't 1, it still wasn't 100% reliable. Is that correct?
Yes. So you see the point here is that we really must come up with some predictions of the fatigue for the specimens and the real structures which are exposed to the various types of loading. So this is the life. So for example, if you take the hull of the ship, then it could be quiet waters, it could be very troubled waters. So it's sort of that's how it is. And then you have somehow to assess the damage. And the simplest possible way to assess is just this linear accumulation of damage, which is this Palmgren concept. But if you sort of start to compare this concept with real life, then you may have the damage. Then this C, capital C, is much less than 1. Let's say, as I say, 0.15. It could be also the fracture, but you may also have a case then this damage equals something like 4, and it's still there is no failure. So this is a concept which gives you some sort of the feeling, but it doesn't guarantee that this is exactly true, that you'll have this failure exactly at 1. You may have it much less, and you may have it much more, but it depends. So there are lots and lots and lots of alternative theories and hypotheses. So if you look up the literature on this, there are tons and tons of the papers which present the results and present some kind of improvements of this concept of linear accumulation of damage. You see my point?
Yes, thank you. But how can it ever be 4? That sounds a bit.
Yes, it sounds very awkward, but that's how it is. So I don't think I'm able to find the research paper which was published in, I think, in 60s. But there was some sort of evidence. And you see, this is something which is very difficult to dispute, because people, they just present the results of their experiments. And then they just say that we follow this concept, and then our specimen failed, then this accumulated damage was equal 4. And then other group of researchers doing another sort of experiments with another specimens, they say that we did the experiments and they have found that the failure occurred, then the damage was 0.15. So it's extreme cases.
All right, thanks.
So I have a question too.
Mm-hmm.
And this is not for the assignments, it's for the exam, is that okay?
Yes, sure.
You said that we have to make some stories, and I'm not quite sure what you mean about stories.
So so let's say that you have drawn you took the question, or let's say this stress concentration. Then if it's not just this line, stress concentration, there will be some sort of clarification. Will be 3 or 4 bullets saying that the difference between performance, it's not like this, but just the difference between the performance of ductile and brittle materials, the influence of different factors, something else. And then you give your answer. Then we just make sure that you sort of tick all the boxes so that you have clearly explained the difference between brittle and ductile materials. You have clearly explained the influence of various factors, and so on and so forth. So this is what I mean by story.
Oh, okay, I get it.
Sergey, do you have any idea whether or not the exam is going to be physical or online now when it's on the 1st of March and the restrictions are till the 28th?
Yeah, but nobody knows. I'm afraid I'm afraid you should ask Mette Fredriksson.
Huh, okay.
Sergey,
Yeah,
is it possible to contact you after this lecture
of course.
in
Of
the
course.
following weeks for questions?
Yes, yeah. Certainly. You can you can use MS Teams, but you can also drop an email to me, and then we'll be in contact with you on MS Teams. Of course, I'm always available.
Okay.
No worries.
Thank you.
have a question.
Yes.
In the solution 10.43,
Just
around
one
the
second. 10.
in the 3, lecture 3.
Probably it's this one. 10.
Lecture 3, I think.
10.4. Oh no, not this one.
Lecture 3.
Yeah, I understand.
Oh, okay. Sorry.
So it's I'm just drawing 10.4. Here. Yes. Right.
Yes. I'm not sure how to find the deflection at B due to the uniform load Q.
So I think that just let me. I'll just take the book.
Yes.
So we have mechanics of materials, and we have the appendices, and we are after appendix. Just let me see what is it G or is it some? Oh,
G or H, I think.
Yes. So now let's just see. We have cantilever. Yes. So we have appendix G. And in the appendix G, you have case 1.
Yeah.
And so you see this picture, right? So this is exactly what we have with this Q, right?
Yes.
So then you see that there is expression for the deflection of the beam. And it goes as minus qx squared divided by 24 EI and then something in brackets. You see it?
Yes.
V equals minus qx squared divided with 24 EI bracket open 6L squared minus 4LX plus x squared.
Yes.
So now we take a look at this picture. And we see that we have here L in the table, but in our case the length of the beam is twice L. You see, you have L and L, right? You see it in the picture. So the total length of the beam is 2L, right?
Yes. Yeah.
So now it means that you have to use this formula for V with small modification. Instead of L, you have to plug in 2L because this is the total length of the beam.
Yeah.
And instead of X, you plug L because the coordinate X equals L, as you can see here. And then if you just plug in this formula X equals L, and instead of L, you plug twice L, then you find this fancy formula 17/24.
Okay. Okay, makes sense. Thank
you. Good. Yes.
Yes, the same thing. The same problem. Why do we use the delta B in one of the solutions, and the other one is the Y deflection?
I'm sorry, I'm not quite sure I follow your question.
Yeah.
So this is the story about the same problem, right? So it's 10
Yes.
for 3. Yes. Okay. So
Yes.
now
The first one, the deflection at B due to the load Q. You said we used the deflection at the Y direction. The first one in Appendix H. But the
Appendix G.
Yeah, I have another addition. The second load, the RB. This one matches up with the fourth one in the Appendix G. But it's not the Y, it's the delta B. How come?
Yeah, so the third thing, let's just clarify that we agree that how the 17 over 24 emerged. So it's emerged from this formula for the displacement V. Then we, instead of X, we substitute L, and instead of L in this formula in the appendix, we substitute 2L. So this is what we agreed upon, right?
See.
Okay, so now the question is, so how this delta comes into the play? So now let's just take a look at I think we have this case form, right? Or rather, probably we can just, it's closer to have this case 5, when you have this P not in the end of the beam, right? So you see this case 5.
Yeah.
There you have cantilever beam and P is applied somewhere. So then you have the formula for V, which reads as minus px squared 6ei brackets 3a minus x, right?
Yeah.
So now you just, first of all, of course, you observe that the force acts not downwards but upwards, so probably we have to change the sign in front of the whole expression, right? Next thing, how it should be written here, but it's all put out. So now the next thing is that we see that our x equals a, and our a equals L, right? Because this is what we have here, that our formula for x for V is x equals L and a equal L. And then if you substitute these things into the formula, you get exactly this result. So it will be RBL cubed divided by 3EI. So I just take a look at the upper formula, not into the formula with delta. I just take this formula for V.
Okay.
So this is how you show it's just consistent. So we use formula for V looking at the case 1, although there are these expressions for delta B and theta B. But we took a look at this formula for V as a function of x. And then we do it consistently in this case 5. We also take a look at this formula for V as a function of x.
Okay. Thank you.
Good. Okay, more questions? So should we say it? Should we call it a day? Well, as I told you, I am available for your questions. Just don't hesitate to contact me. So I also have some other courses, so I might be involved in the teaching, but if you just drop an email to me or send a message via MS Teams, for sure we'll find time to discuss questions which you have. So please just don't hesitate to contact me if you have any questions. And of course, I wish you good luck with the rest of the course and with the examination, and hope to see you soon. So bye for now.
All right, thank you.